Assalamualaikum and good morning, everyone.
Waalaikumsalam. Good morning, sir.
Waalaikumsalam, morning sir.
Okay, so before we go into tutorial related to trust, I think Dr. Jana already taught you guys until chapter on trust, right? So let's recap a bit on what formulas that you need um, to have, okay, or to have for this chapter on trust. Okay, so assume that your trust is your one element of trust has this kind of arrangement, okay, with an angle theta from the x-axis. And the first node here at this one, the first n here, the node value is you always assume that this is smaller than this node. Okay, for example, like this node is given as number 1, while this one is number 2. So let's say if this node is number 2, then this node here at the other end will must be higher, either 3, 4, or and so on. Okay, and the angle theta must measure from the x-axis, the positive x. Okay, so the first formula that you need to remember or to jot down is this formula K. So K equals E, the Young modulus, times area, cross-sectional area of the bar, divided by the length of the bar, multiplied by the matrix of cosine and sine. Okay, so C represents cosine and S represents sine of this angle. Okay, so this is the first formula that you need to remember. Okay, so K is the stiffness matrix of one element. Okay, one element of the truss. And then the next formula that you need to remember is how to find the strain within the bar. So epsilon equals 1 over L times this matrix of cosine and sine of the same angle multiplied by the displacement. Okay, so u1x and u1y represent the displacement of the first element of the smaller element number, node number, sorry, and u2 and u2x and u2y is the displacement of the next node. Okay, and then the next formula that you need to remember is how to find the stress. So stress is just stress equals Young modulus multiplied by strain. And then to find the tension, T equals Young modulus E times A times epsilon. Okay, so you have 4 formula that you need to know, okay, or remember for trust, yeah. And of course, you need to know this relationship. Force equals K times D, displacement. Okay, so let's go on looking at the tutorial question one by one. Okay, so question number 1. So figure 1 shows a pin jointed plain truss, structure discretized with 2 elements and 3 nodes. Okay, so elements are the bar. So it's already given here. Number 1 is the bar number 1 that has node 1 and node number 2. And then element number 2 is the second bar which has element number 2 and node number 2 and node number 3. And a load 5 kilonewton is applied at node 1. Okay, so it's applied upwards. So the question asks, evaluate the structure for global stiffness matrix and displacement for each node. Okay, so let's find the stiffness for each stiffness matrix for each of the bar, and then we combine it to find the global stiffness. Okay. Okay, so before that, we need to determine the angle made by each of the bar. Okay. So let's look at bar number 1 or element number 1. Okay, so this is bar number 1. So you need to look at the angle made by the node number 1, okay, the smaller node. Okay, so in this case, you need to measure the angle from positive x. Okay, so you need to find this angle. Okay, so the length given is here 6 square root 2, and then the yang modulus and area is also given here. Okay, so from here you can find the angle theta by using cosine and sine, okay, trigonometry. Okay, so in this case, because the height here and the length here is the same, okay, 6 and 6. And so this angle is 45 degree. Okay. So same with this one, meaning that the angle theta is 315. Now let's look at the second bar. Okay, so you need to find this angle because it is made by the smaller node, number 2. So again, the height here is 6 and the length is also 6, okay? So the angle theta is 45 degree. When you know the angle already, then you can start calculating the sine and cosine for each of the element. Okay, so it's better if you can make this table so that later on when you want to develop the stiffness matrix, you can just look at this table, okay? Okay, so first length is given by 6 times square root of 2. So the length for each bar are the same, okay? And then angle for element number 1 is 315. And for element number 2 is 45. Then you can calculate for cosine and sine. So you get square root 2 over 2. So sine 315, you get negative square root 2 over 2. So cosine square, you get half. Sine square also half. And then cosine times sine, you get negative half. Okay, so repeat the process for element number 2. Okay. Then you can start assembling the stiffness matrix for each of the element. Okay. So we start with element number 1. So element 1, K for element 1 equals E A over L for element number 1. And then we use the formula here. Okay, so we use this formula. So we just plug in the value from the table. Okay. So I prefer to factorize half because everything has half in the cosine and sine. So just factorize half and put it here. Okay. Then you can simply put the remaining number inside the matrix. Okay, so in your stiffness matrix, always start with U1x or the smaller u followed by the higher u, okay, higher displacement. Okay, then you just plug in with the number in the table. So before you proceed, make sure that the stiffness matrix is symmetric. Okay, so symmetric means the value is has a mirror image, okay, about this diagonal line here. So if you look at this, -1 equals -1 on the other side, and so on. So if your stiffness matrix is symmetric, then it's correct. But if it's not symmetric, then please check again before you proceed. Okay, so make sure it's symmetric. And now we can create the stiffness matrix for the second element. The same formula, and just plug in with the cosine and sine. But first, label, if you prefer to label it the displacement, it's better, okay? So here the element is, in the element number 2, we have node number 2 and node number 3. So we label using displacement on node number 2 and displacement on node number 3. Then just plug in with the number. Okay. So also make sure that this matrix, stiffness matrix is symmetric before you combine them together. So the question specifically asks for global stiffness matrix. So global stiffness matrix meaning that you need to find the overall stiffness for the system, okay? So you just combine them together. So K equals E A over 2L. So L1 and L2 are the same based on this table. So we just, we assume it equals L. So now we have 3 nodes, meaning that we have a global stiffness matrix of size 6 by 6, okay? Okay, so you just plug in the stiffness matrix based on the displacement of each node, okay? Okay, so before that, you need to look at the common node. So here the common node is node number 2. Okay, so node number 2 is shared by both of the bar. So it's better if you can fill the global stiffness matrix with the nodes that are not common, okay, like node number 1 and node number 3. So you fill the matrix with these 2 nodes first. So you want X, you want Y, and you want X, you want Y. This 4 value here is the same as this 4 value 1, minus 1, minus 1, and 1. And this U2X, U2Y, and U1X, U1Y is this 4 value here. And so on, okay? Okay, so we have the common node here, U2X and U2Y. So you need to add up this this value 4 value here with this 4 value here. Okay, so you get 1 plus 1 equals 2, 1 minus 1, 0, 1 minus 1, 0, and then 1 plus 1 equals 2. So this is your global stiffness matrix. Then after that, you need to assemble the displacement vector or displacement matrix. So we have 6 displacement because we have 3 nodes. So each node has 2 displacement in x direction and also in the y direction. Okay, then you apply the boundary condition based on the figure. So we have roller support at node number 1. So for a roller support, here at node number 1, the movement is allowed only in the vertical direction, okay, but not in the x direction. So you have u1 u1y, but 0 u1x, okay, because you cannot move it in the x direction. So we have 0 here, and then u1y. And then on the second node, also roller support. So here in this second node, the roller allows the node to move in horizontal, okay, in the x direction only, but not in the y direction. So here we have u to x, but 0 u to y because it cannot move in vertical direction. And then lastly, at node number 3, for this support, the node cannot be moved in any direction, okay, except for rotation, okay. But in for translational, it cannot move in either x or y direction. So meaning that the displacement for both u3x and u3y are 0. Okay, so the question asks you to find the displacement for each node. Now we have we only need to find u2 u1y and u2x. Okay. And now we need to assemble for the force matrix or force vector. So here we have f1x, f1y, f2x, f2y, f3x, and f3y. Then similar to displacement, we need to apply the boundary conditions given in the question. So for the first roller support, so we have a reaction force in the x direction, okay? So we have f1x, but 0 f1y. But since we have an applied load here, 5 kilonewton in the y direction, so we have f1y equals 5, okay? Because of the applied load. And then for the second node, we have reaction force in the y direction, but no force in the x direction, okay? So here we have 0 f2x, and we have only f2y. And then for node number 3, we have forces or reaction force both in both direction, in x and also in y. So we have f3x and f3y. Okay. Now we have the 3 matrix here, K, U, and F. Then we can find, calculate for the remaining things that we need to find, which is the U1y, U2x, and the forces. So the first question asks for the displacement. So let's find the displacement first, okay? So K KU equals D. Sorry, KU equals F. So we need to find U1Y and U2X. So we just create or take the matrix for the second row and the third row only, okay? And multiply with U1Y and U2X. So if you look at this, the stiffness matrix K, the second row, multiply by U, you will get okay, so minus 1 times 0, 1 times U1Y, 1 times U2X, minus 1 times 0, 0 times 0, and 0 times 0. So you need to look at, you need to remember how to do matrix multiplication, okay? That you have learned maybe in form 4, okay? And then the third row, you only take this value 1 and 2. And then equals F. So F here, you only take the second and the third value or the third row. Now you can solve this simultaneously, either using calculator or using Gauss elimination. Okay, so in calculator, so you can use your calculator by so if you have Casio 570 ES, you can solve the matrix simultaneously. Okay, I'm not sure whether you know how to do this, but I just show you anyway. Okay, so tak nampak. Okay, so in your calculator, so if you have Casio 570 ES, so you just simply click mode and then press number 5 equation, and then choose number 1. Okay, the first selection in the equation, which is a n times x plus b n times y equals c n. Okay, so if you choose that, you can simply fill in the value in the matrix here. So you have 1 and then 1 and then 5 and 1, 2 and 0, and then you simply press equals, then you get both value for u1y and u2x. Okay, oh lupa. Okay, so I forgot to multiply with EA over 2L. Okay, so here we have EA over 2L. Okay, so let's rewrite this. Okay, so EA over 2L you get, so you just substitute the value given in the table. So E is 200 square root 2 times A equals 3 divided by 2 times 6 square root 2. So you get 50. So we calculate, then you get here 0.1 and 0. Okay, solve simultaneously. So please don't do it manually, okay? It will take quite a long time. Try to use calculator or use online kan, test. So guna symbol lab, okay? So here you will get U1Y equals 0.2 and U2X equals negative 0.1. Okay, so until here, now you already solved for the first question for the displacement and also for the global stiffness matrix. And then the next question asks you to determine the internal forces for element number 2. So only this element. So the question asks you to determine the internal forces. Okay, so the internal forces meaning that the forces acting on the bar, okay, not in the component, okay, not F2Y, F3X, and F3Y. You need to find the overall force acting within the bar. So here you need to use the formula related to the strain, which is this one. Find the strain first, and then find the tension within the bar. Okay, so let's find the strain for the second element. Okay, strain for the second element equals 1 over L times times negative cosine, negative sine, cosine, and sine. So you just fill in the second the value from the second element here. So you get negative square root over 2 and then multiply by the displacement. So you have U2x, U2y, U3x, U3y. And then substitute the values. So you get so U2x is already calculated. So you get negative 0.1. And U2y, U3x, and U3y are all zeros. And then you can calculate this. So you get 1 over 12 times minus 1 times minus 0.1. So you get 1 over 120. So this is for the strain on the element number 2. Then from here, you can calculate the tension, okay, or the internal force. So tension on the element number 2 equals E times A times strain on the element number 2. So just substitute the value. So you get 7.07. So the unit is in kilonewton. Okay. Okay, any question before we proceed with question number 2?
Doktor nak tanya,
Yep.
kalau theta tu kena ambil daripada positive x-axis kan?
Yes. Always take theta from positive x-axis.
Okay.
And always take theta from the node with lower number. Okay. So for example, 1 and 2, we take theta from node number 1. Okay. And then from positive x. And for the second element, we take theta from node number 2 instead of node number 3. And then take it from positive x. Okay, lepas tu baru kira cosine sin lah. Lepas tu nak jadi apa? Tu pandai lah. Okay, the calculation will get messy when it comes to calculating the displacement. Okay, but I think if you can manage to calculate like K1 and K2 up until here, it should be okay. Yang bawah ni more towards mathematics lah.
Okay, thank you.
Okay, any more question? Rasa macam di dunia baru kan? Bila masa lah belajar Truss ni? Aduh. Okay, so let's look at question number 2. Okay, 925. Okay, so question number 2. Consider the truss shown in figures below. The elements have cross-sectional area A equals 645 millimeter square, and then Young modulus E equals 100 gigapascal. Okay, and then the length for each element are different. So you need to calculate the element, okay? The length. So determine the global stiffness matrix of node number 3, and then displacement at node number 3, and also stress in each element. Okay, so let's determine the stiffness for each element first. Okay. Okay, so let's look at let's name the element. Okay. So here in this question, in the figure, it only gives you the node number like 1, 2, 3, and 4, but no element number. So you need to name it yourself. Okay. So in this case, I will name this as element number 1, and then this is element number 2, and then the last one is element number 3. Okay, so let's look at element number 1 first. Okay, so in this element, we don't have the length of the bar. So you need to determine the length of the bar. Okay, so this you need to use trigonometry that you have learned since form 1. Okay. So here we have 60 degree in the middle angle and 30 degree here. So assuming that this is 90 degree from 1 to 4. So of course, the remaining degree here is 60, okay? So it's a no-brainer. It's 60, 60. Then the remaining degree is also 60 degree. Okay, so dia segitiga sama sisi, okay? Equilateral triangle, kot nama dia. So the length is 1.8 on one side, meaning that the other side is also 1.8 meter. So the length here is 1.8 meter. Now we look at the second element. Okay, so this is 60 degree, and node number 2, node number 3. And then the length is 1.04 meter. Okay, so we need to use this angle in your calculation of cosine and sine. So this angle made from x-axis is equals 120 degree. Okay, now lastly we look at element number 3. Okay, so we need to use this angle, and then the length is also 1.8 meter. Okay, so this angle so this is 90 degree, and so this is 30 degree. So the angle made by node number 3 is 150 degree. Then you have all the angles and the length. Then we can create the table of cosine and sine. So element number 1, the length, theta, cosine, sine, cosine square, sine square, and cosine times sine. So the length is in meter. So we have 1.8. Angle is 30 degree. Okay, so for the first element, angle is 30. So just use calculator to determine cosine and sine. Okay, now we repeat for element number 2. So element number 2, the length is 1.04 and the angle is 120. And then determine the cosine and sine. Okay, and lastly, element number 3, the length is 1.8 and the angle is 150 degree. And then determine the cosine and sine.
Doktor nak tanya,
Yep,
yang elemen 3 tu kita ambil sudut dekat tu
dekat
Dekat
node 3.
Node 3, bukan node 4.
Bukan, sebab we always take the angle from the smaller node number.
Okay.
Okay, so 3 dengan 4 kita ambil angle dekat node number 3. Okay, now we have the table. Then we can calculate the stiffness for each element. Okay, so let's calculate for element 1. Okay, so because the length for each element are not the same, it's better if we can calculate the EA over L. Okay, EA over L for each element first. Okay, so let's say we name it K bar element 1 equals EA over L1. Okay, so we get 645 times 100 gigapascal divided by length. So we assume or we take everything in millimeter. Okay. Instead of converting to meter, we convert everything to meter. Okay. So the length becomes 1,800. Okay. So you get 3.58 times 10 power of 10. Okay, unit dia Newton over millimeter. But I think if you don't put unit, it's still acceptable. Okay. And then for element number 1, we assemble the matrix. So assemble the matrix according to this formula. So K1 equals K bar 1 over 4. So Y4, I simply factorize this 4 here from cosine squared and sine squared and cosine times sines. So later, when you fill in the matrix, you will have everything over 4. So factorize kan. Okay, you will see it if you do it manually. Okay. Now assemble the matrix. So for element 1, we have node number 1 and node number 3. So in your matrix, it represents the displacement of 1 and displacement node number 3. Okay, so just fill in the value here from the table. Okay. So this is the stiffness matrix for element 1. Now we go to element number 2. So similar step, we calculate the EA over L. So we get 6.20 times 10 power of 10. Okay, then we assemble the matrix. Okay, so this matrix represent for node number 2 and node number 3. Then just fill in from the table. Okay. Now we repeat for element number 3. So we get then we assemble the matrix. So this represent for U3x, U3y, U4x, and U4y. And then fill in from the table. Okay. So the first question A, determine global stiffness of node number 3. So I think this one you need to find the global stiffness only at node 3. So you don't need to assemble a 4x4 matrix. Okay, you'll be like satu page A4. So you just need to find the global stiffness at node number 3. So at node number 3, so the stiffness, this stiffness at node number 3 equals, so you just add up all the values for element number 3. Okay, so first we look at the first matrix. Okay, so we take this value, these 4 values only. And then in the second matrix, we take these 4 values. And then lastly, in the last matrix, we take these 4 values. And then you add up element by element, okay, of the matrix. So you get so 3 times K1 bar over 4 plus K2 bar over 4 plus 3 K3 bar over 4. And then you get this one minus square root 3 K bar 2. Similar. And then this one you get K1 bar over 4. Okay, sorry, this is over 4 plus 3 over 4 K bar 2 plus K bar 3 over 4. And then substitute the values and you get 6.93 minus 2.68 okay, so this is the global stiffness matrix for node number 3. And then the second question asks you to find the displacement at node number 3. So first we need to assemble the displacement matrix or displacement vector first. Okay, so if you look at node number 1, it's a support, a fully support. So there will be, the node will not move, okay, cannot move. So the displacement of node number 1 are 0. Okay, similar to node number 2. And then for node number 3, it can either move in the X or in the Y direction. So you have U3X and U3Y. And then for node number 4, is similar to node number 1 and number 2. So no displacement. Okay, so this is the displacement matrix. And then assemble for the force matrix or force vector. So you have F1x, F1y, F2x, F2y. And then for the x, for the node number 3, you have 10 times 10 power of 6. 20 in the x direction. And in the y direction, you have 10 power of 6. And then for the node number 4, F4x and F4y. Okay, so the question asks you to find the displacement at node number 3. So you just take this value and multiply with the global stiffness matrix of node number 3. So you have okay, so you use your calculator, you get U3x equals 4.16 times 10 power of negative 4 millimeter. And U3y, you get 3.28 times 10 power of negative 4 millimeter. Okay. And then the last question, you need to calculate the stress in each element. So what you need to do is you need to determine the strain first, okay? So strain element number 1 is 1 over L1 times negative cosine, negative sine times positive cosine, positive sine. This formula. Okay, so you get okay, so element 1, you have displacement of node 1 and node number 3. So node 1 is 0, no displacement. So you have displacement of node number 3 only. So calculate and substitute the value. You get strain equals 2.91 times 10 power of negative 7. And then you find the stress. So stress of element 1 equals Young modulus times the strain of the element 1. So you get 29.1 kilopascal. Okay, then repeat for element number 2. Okay, negative cosine, negative sine. Multiplied by displacement of node number 2 and node number 3. So you get negative 4.73 times 10 minus 7. And then the stress equals negative 47.3 kilopascal. Okay, and lastly for element number 3, okay, so the displacement is for node number 3 and node number 4. And be careful with the arrangement. So you start with the lower node first, the lower number. Then you get this equals 1.09 times 10 power of negative 7. And then the stress equals 10.9 kilopascal. Okay, any question before one more question, one more tutorial question?
Tu tengah tanya dekat global matrix tu.
Yep, boleh.
Mana tengok atas. Atas kira tu. Ni global. Global matrix kat note 3.
Sekejap. Ni tak
Yang tu
berapa.
tu.
Yep.
Apa kena erat dengan stiffness 212?
Mana? Ni
Susunan matrik ni.
Okay, so you just add up the element from this one. 3, square root 3, square root 3, 1. Darab K1 over 4 plus 1, negative 3, square root 3, negative square root 3, and 3 times K2 over 4 plus this one, K3 semua ni, dan K3 over 4. So jangan lupa ada kat depan ni, berkali je. Tadi kita dah factorize. Kalau tak nak factorize, kena masukkan dalam matrix. Tapi dia akan jadi in decimal points lah. Boleh meningkan kepala. So ni nak kurangkan pening. Faham kot?
Okay tu.
Okay, so I leave it to you for question number 3. So you can try yourself. So question number 3 is quite straightforward because it requires you to determine the displacement only at node number 1. And question number 4 is your quiz. You need to submit by tonight, okay? Before 12 a.m. Okay, any question before we end this lecture? Okay, so if you don't have any question, we will meet again next week on new lecture. If any question related to yes.
Video ni boleh post
nanti dekat YouTube. Nanti
okay.
saya bagi link.
Thank you.
Okay. So that's it. See you again next week same time, okay? 8:45. Assalamualaikum and goodbye.
Thank you, Doktor.
Waalaikumsalam. Terima kasih, Doktor.
Thank you, Doktor.
Thank you, Doktor.
Thank you, Doktor.
Thank you.